In this video, we're going back to two variables for a moment, and we're going to introduce a new notation or a new terminology that is actually what we've seen before, but it sounds different and sometimes it's written a little differently. So we just wanted to go over it in a specific example. We've already looked at the tangent plane, where we describe it as our curved surface being approximated by a tangent plane here. Notice that this is a linear function. So tangent plane or a linear approximation. We could also write that if we move this term to the other side, we'd have a difference between two f values. And notice that x minus a is a difference between two x coordinates, so it's delta x. Y and b are both y coordinates, so we can often call that delta y. And we get an alternate form of this relationship. The key thing is there's no difference in the ingredients. It's just a question of how you package those differences. Now, the calculus idea is that if we let delta x and delta y get smaller and smaller and smaller, some people approach this and think of that as approaching dx and dy. We've essentially done that when we looked at integration back in the day. Now, we would call those dx and dy differentials, and we can actually think of them as infinitesimal changes in x and changes in y. When we do that, we would also get our delta f turning into what we'd call df in this differential notation. And in principle anyway, if these were infinitesimally small, we would get this relationship becoming an equal sign, whereas on the last page, it was an approximation. Now that's all well and good. This is a nice compact way to write this relationship, but in practice what we're going to do is use finite delta x's and delta y's, and we're basically going to be using this approximation here, but you may see it notated with dy, dx, and df if people are thinking, as long as things are really, really small, we can represent that as an equality. Thinking about this sentence, this is often termed or seen as a formula for the change in f for a small change in x and a small change in y. For a function of three variables instead of two, the local linearity works in exactly the same way. If we think of it as approximating our function, we have a term for x, y, and z and the differences in those, which we can write explicitly as the change in f. Again, if we bring this term to the other side, it goes negative, and we get a change in f on the left, and then what's left on the right are changes in x, changes in y, and changes in z times the respective derivatives. Or we can take that approximation sign and replace it by an equal sign if we go down to the differential form, where we think of these as infinitesimal changes in x, y, z, causing an infinitesimal change in f. The only difference between these or the two variables and the three variables is adding one more term to each one. We'll see in later videos how we'd actually apply this or try to use this in modeling or in other applications.